Thank you. First of all, I like to say I appreciate coming here. I've always enjoyed coming to Stanford events, and certainly I think this promises to be an interesting time because obviously you all have a very keen interest in this, and it's something that we at AMD take very seriously, and we think it's got a huge future. So, first of all, just to introduce myself, I'm a fellow at AMD. I focus on three different things: imaging, computer vision, and deep learning. I'm the domain architect for all of those, and which means that I more or less innovate the various architectural approaches that we want to take on the various platforms that we provide to our customers, both on the hardware side, the architectural side, and the software side. So I'm deeply involved in this. Originally, Mark Papermaster was supposed to come, and unfortunately he had some other obligations, so he asked me to step in. And the only reason I'm mentioning that is that he is by far a better speaker than I am with respect to what we do in the various products that we have, namely Zen, Vega, Navi, and beyond, and so forth. He can speak about those much better than I can. But the talk here today is about really more on deep learning as it relates to Zen, Vega, the architectures that we have coming up and beyond, and how we think about the various challenges that exist in deep learning, not just at the big scale, but at the small scale. So there's lots of really interesting topics, and what I'll try to do over the next hour is to try to give you an overview of this. This is by no means a technical deep dive. I do have some material on that, and generally those talks go for several hours, but this is more to try and understand, what the relationship is between the challenges of deep learning as they exist today and how we expect them to evolve over time, and the kinds of compute power that we have available to address them and to provide users with reasonable experiences and reasonable outcomes. So, before I get to the agenda, what I thought is maybe talk about some of the things that we actually want to experience. So deep learning is a very abstract thing. You want to give it some data, you want to teach it something, and then you want to be able to extract classifiers and so forth. And that's all interesting, and for those in academics, that's the thing that we really focus on is the errors, how many epochs, what's the training converge rate and so forth. But for general users, what you really want is the demand for better experience. And so there's a couple of examples here, and everybody's familiar with VR and sort of the new age of experiencing what we call embedded imaging or immersive imaging and things like that. So the question then is, what does it take to give you good experience in those kinds of environments and those kinds of applications? And while that may seem a long way away from deep learning, it actually has some very, very close kinds of things that require the development of useful products and capabilities within these experiences. So while it looks simple and everybody's done it and sort of experienced it, getting it good and getting it reliable and getting it robust is actually pretty hard. So this is one example. The other example is that we are kind of in an age now where there's this mounting demand for compute power and capability to handle very large data sets. And this is not going away anytime soon. The advent of the internet with the ability of high bandwidth communication to and from the cloud gives us the sense that the amount of data that's going to be there and available is enormous and growing at a very, very rapid pace. So the challenge here is, what do we do with all that data, and how do computers in the server class systems deal with that kind of data challenge? And it's not just the amount of data, it's the timing, it's how quickly can we turn that around and give us a result that we're looking for. The poster child for this, of course, is Google, where every single query that you make goes through a series of deep learning inference kinds of decisions, and over time it learns how to give you the best query in the quickest time in the right order of importance. That's all an example of deep learning. It's under the covers, nobody knows about it, but In fact, it is deep learning in a very, very large scale. So with that in mind, I'm going to cover 5 topics. I apologize ahead of time that some of these are going to be rather abstract because I don't have enough time to get into detail. However, it's suffice to say that we believe we've done our homework. We believe we have looked at the problem closely. We have evaluated all of the parameters that are available to us, and we certainly recognize some of the limitations that exist. So I'm going to go through compute trends and challenges. This is not specific to deep learning, but deep learning is sort of the customer of what it takes to do all of this. And then I'm going to talk about deep learning opportunities, and with the idea that every one of these opportunities creates a demand or some kind of an ask on the side of computers and software and algorithms. So we'll review that for a little bit. And then finally, to tie it all into the kinds of products that AMD is doing with respect to our software stack, our 2 different classes of hardware, mainly Zen, which is the x86, and Vega, which is in our GPU class. If you have questions, I'd be happy to answer them. However, I guess the best way to do this is to perhaps wait until the end. Is that, Andy, is that okay with you? Yeah, that's my choice. All right, well, whatever. I'm easy, so don't be afraid to. Okay, so this is sort of a cartoon, really, of data points that reflect where we are in various metrics with respect to computing. And the details aren't really necessary to understand, but what is interesting to note here is that everybody's sort of said, well, Moore's law is sort of over, and we're getting to the point where we just don't get enough bang for the buck anymore the way we used to. The amount of transistors per square millimeter is leveling out, and so forth and so on. And this is all generally true. More importantly, we're reaching a point where we can't run these chips any faster. We're at several gigahertz now. It's just not possible to run them faster without sacrificing something else, and usually that something else is power. There have been many attempts to sort of scale it in a different direction by going into multi-threading and multi-core and so forth, and you can start to see that emerge right around 2010. And certainly there's some success there. We wish there was more, but the fact is we have enormous amounts of legacy code which doesn't fit well into the multi-threading kind of multi-core approach. However, it's there for the taking, and we get a certain amount of benefit out of it. The next issue is cost. I actually can remember the days when, if we tape out 180 nanometer, we thought, wow, that's really expensive. That's $5 million. Today, those numbers are long gone. So we're in the age now of 7 nanometer. There are some experiments and some work to go even below that. The fact is that this is what it takes to be competitive in the advanced semiconductor world. And AMD participates this as aggressively as anybody else. But the problem is that, as you can see, and this is really just a relative scale, but the cost to do this is quite significant. It's many tens of millions of dollars to do a tape out these days. So you can't get it wrong. You have to do it right. And that means that we have to do enormous amounts of work on the front end to do the regression and validation. So welcome to Moore's Law Plus, and the idea behind Moore's Law Plus is that, well, we acknowledge all of those things we just talked about, and then build on the idea that we'll start turning other knobs, right? We'll turn knobs on integration, we'll turn some knobs on process integration, or process technology. We will definitely turn knobs on system design and software, and we will, treat it as a whole to build different types of systems using the building blocks that we have from the traditional way and some of these new ideas that are intended to help us through the system integration problem. So there are a number of different ways in which we do this. I won't go through this in detail, but the point is that for each one of these ideas, we've developed a shopping list of sorts that can help us. And I'll go through a couple of examples, but it's important to note that we are not afraid to say, all right, yeah, Moore's law might be sort of dead or not moving as well as it used to, but we're going to be just as aggressive to move in directions which help us build bigger, better, more higher performance and lower power systems, despite some of the limitations that exist as a function of the traditional Moore's law. So obviously the foundation for all of this is sort of the underlying silicon technology. There's a lot of work going on to figure out how to do this better, how to build more advanced technologies in the transistors, the FinFET, interconnects, power gating, all sorts of things that come into play here. While we participate on that, we rely a lot on the fabs and the semiconductor equipment makers, but jointly there's a lot of work going on to help us through that, and we expect to have pretty substantial improvements over the next 10 years or so. In a similar way, memory technology has sort of stalled out. We're getting more dense memory, but it's not progressing at the same rate as it used to, even as little as 5 years ago. So we are trying to figure out how to take advantage of the fact that we can still get more memory and we can still get reasonably good speed, but the trick is more in packaging. So AMD was the first major company to introduce HBM packaging. It was available on our Fiji class GPUs, and it's the first time we now start to see three-dimensional packaging and three-dimensional circuits appear in very, very high performance types of systems. I'll explain in a minute. Yeah. So so the idea here is that you want to be able to access memory very, very quickly through shortening the distance between the interposer that's driving it and the actual memory component, and HBM stands for high bandwidth memory. And there are a number of different initiatives here. This is the first one. There's HBM2, there's a CCIX standard, there's a whole bunch of things now starting to emerge in the sort of processor memory interface and boundary to ameliorate the problem of the sort of natural delay and overhead, including power, between the processor and memory. So this has been shipping for some time, and it's very successful. We have a number of programs now to take it to the next level, including some advanced packaging and testing. Sure.
How many DRAM chips can you stack on top of each other?
That's a good question. I honestly don't know. The more the better. The picture shows 4. I would imagine it's some low number like that. There's a limit, of course. You can't. There's a power dissipation issue and all sorts of things, as well as you can't. It'll fall over. I mean, the interconnect reliability and manufacturing, all sorts of things you can imagine.
Keep the processor from cooking it.
So a lot of these are liquid cooled. So yeah.
Really?
Yeah.
Are you doing immersion or are you using contact?
Heat pipes. Yeah, we have. I mean, these modules. I think I have a slide later that shows the total power dissipation of the entire card. It's in the hundreds of watts, so it's quite warm. Yeah. That's what it takes. That's what it takes. Yeah. So anyway, okay. So I mean, that was just a very brief, summary of things that we are doing on the technology front. But as I mentioned in the beginning, this is all about experience. At the end of the day, what we really want is users to have a good experience. And the good experience in imaging and in video and computer vision and so forth is all about what you see and what you experience as a function of how the computer generates things or how the sensor captures things, or how the interaction is, for example, in AR or VR. And so this is just a sort of a brief history of, how things have occurred over the last, 20 or 30 years. And the idea here is that we believe going forward that the idea of immersion of vision is something that's going to be very important for users, whether it's in watching movies, or if it's in education, or it's in healthcare, or whatever. The idea of being able to immerse yourself and view things as if they were in the real world is sort of the ultimate goal. And there are a number of challenges and obstacles to get there along the way. However, the common denominator is that they all require enormous amounts of compute power. When I designed my first digital camera many, many years ago, sort of the metric was how many operations per pixel did you actually end up using in the system. And we were lucky if we could count 100 or 200 operations per pixel. Today that number stands at around 2,000. So we think it's going to go to 2 million pretty quickly. So imagine that in a 4K video, you have to process every single pixel with 2,000 or so ops, and then add that up and figure out how many frames per second, ops per second you actually have to do in order to meet that. So the demand on the system for pure compute power with respect to computer vision, machine learning, and so forth is really exploding. And then when you multiply that by the amount of data that I was talking about earlier, you can imagine the amount of compute power and memory that you're really going to need to address this. In a similar way, deep learning has a kind of a similar history, although it's a little bit disrupted because of what happened in the early 70s, 80s, and 90s. But if you go back and look at sort of the history of who did what and so forth, there's great contributions by Hinton and LeCun, and then finally Krzyzewski and Ronzato and so forth. These guys have all contributed greatly to where we are today with respect to machine learning and what we now call deep learning. But if you look at kind of the last big jump where CNN and DNN became sort of the standard by which most deep learning algorithms were either used or judged, that sort of happened in the 2012 timeframe, and specifically with Krzyzewski's seminal work. And this is the era that I like to call train to learn. So we're actually training systems to learn the data. And this has been now the science of what's been happening over the last 5 or 6 years. And we're entering into an era now where we're starting to see some very complex, deep learning systems that can do remarkable things. And we're getting to the point where it's reliable enough to deploy it for real live applications. Up until a few years ago, this was largely the domain of the academic community because all you really cared about was how well did you score on ImageNet. Well, it's an interesting topic. However, it doesn't really mean anything if you're trying to put together an automobile that needs to understand where the stop sign is. So we're now getting to the point where these systems are becoming very complex and relevant for real applications. And then finally, way off to the right is sort of what I call the ultimate in deep learning. And now we're getting to the era where the machines are learning to train. So you want to be able to tell the system, I don't even know how to build the right structure of different levels of convolution and ReLU and all these other steps in between, but I've got a bunch of data and I want you to learn how to use it correctly and give me the right answer. That's sort of nirvana for us, and we have lots of work going on to get us there. I don't think we're going to get there within the next 5 years. However, it is sort of the ultimate goal is to have a system that can learn to train itself. So lots of applications, and so now we're starting to get into why we have segmented certain things in the way we have. with the idea of trying to come up with products now that can actually do something reasonable with these applications. And this is just a short list, but you can imagine that for every one of these, there are questions you want to ask about what's the best way to use the data I have to answer the questions I have about classification, recognition, detection, motion, any number of parameters that might be interesting for those particular applications. And the answer for almost all of them is build me a good deep learning system, and that should do the trick. Unfortunately, that's better, easier said than done. And so we come to the famous Gartner curve. Some of you may remember, most of you I imagine don't, but artificial intelligence, which is the pseudonym for deep learning now, was very popular back in the early 70s, 80s, and so forth of the last century. And it had a huge hype. Everybody thought this was the next big thing. Lots of work being done, only to come to a crashing conclusion that it doesn't work, it's not fast enough, and it's not reliable enough. So it kind of fizzled out over the next 10 or 15 years. Nothing much happened. Around 2006, LeCun did some really good work to say, well, let's just study a very elementary problem and see if we can make that work. If we can make that work, perhaps we can scale it. And with his work in the MNIST database, that kind of started the ball rolling to get us back up to some interest. And now we're kind of in the slope of enlightenment. These are Gartner's words, not mine, but I mean, this is a very famous curve that's applied to all sorts of different rise and fall of great ideas over time, and it's actually well taught in the MBA school. But the idea here is that we're kind of in year 5 of this trough of disillusionment all the way up through the Enlightenment. Now the question is, does it keep going, or does it plateau out and just become another, or maybe go down again? I don't know. Hard to say. Nobody can predict except a smart system with deep learning, and then it can teach itself. So the point.
Put that curve into the deep learning and see.
Well, that's what I was just saying. The deep learning might be able to figure out if there's a future. Yeah, right. So we don't know, but we do know that we've learned a lot, and hopefully with some continued work and development, we'll start to experience some great success. So I'm going to spend perhaps 10 minutes or so, 15, going through why all of this stuff works. And this is a very simple example. If you were to take a pattern matching problem in the 1990s and say, tell me how to create a set of vectors which describes that picture, you would basically build a feature extractor, which was nothing more than a bunch of pattern matching filters, and then try to figure out a common trainable classifier at the end. And this was really the foundation around which a lot of the computer vision technology worked over the last 10 or 15 years. Later on, it's very natural to say, well, that's not really a car. It's a bunch of components taken together that make a car. And so why don't, instead of building feature extractors, let's build something that can extract out pieces and parts of it and then put that together in some form of a logical order and then come up with a trainable classifier. And so this was sort of the beginnings of shallow network development, and we sort of had the merge of computer vision and early shallow learning. So SVM, for example, was a great way to do this. And then finally, deep learning theory came along and said, well, let's take that one step further and say, well, what we really want is to break down the original image into a whole bunch of very, very simple components, and then gradually build a system where those small components get merged together to build combinations of small components and so forth, until we get to some representation of high-level features, which is now organized along the lines of putting together vectors that eventually can be put into a trainable classifier. And this is really the simple foundation around which almost all deep learning systems work today. And so this is really kind of a simple version of this. These are actual feature map outputs. So in the early stages, you can see these are very simple, just looking for edges, looking for simple patterns. And then as you get more and more into the depth of the network, they start to take shapes. And then ultimately, they begin to take Gaussian level type shapes toward the end, which ultimately, when we feed it into a fully connected part of the network, we can actually determine the final classifier probabilities. So what happened? If you had a system in 2010 that had a 28% accuracy rate, you probably would say, that's fine, but I think I'll pass if I want to make an application. And then starting in 12 with AlexNet, all the way down to, not this past year, but at the end of 2015, the accuracy rate, this is on ImageNet, got to the point where it's within the human error capability. In other words, if you were to show a human the same set of images and say, what is that, how is it classified, the error rate would be somewhere in the neighborhood of 3 to 5%. So we're well within the error of what a human would be able to determine given the same set of tests. That's a remarkable improvement. And if you think about it, prior to this, you were lucky if you saw 30% or 40%. But in the span of 5 years, we've reached all the way down to human discernible errors. And this is a truly remarkable achievement. Now, this is not for everything. There happens to be a very specific set of ImageNet types of things. But the point is that this is now the template around which almost every single deep learning algorithm is being developed.
I want to know the hardware, software cost to prepare.
Oh, good question. Yeah. Yeah, good question. So I don't have the numbers for the order of magnitude is weeks. Yeah, weeks on the other guy's GPU. So.
On a single GPU or what?
No, those were clumps of GPUs. Yeah. Yeah.
How big are the clumps?
Racks.
Yeah.
Racks.
I mean, think about it. So I'll give you the numbers for AlexNet, and I have a slide that shows the rest of them. But on AlexNet, there's 60 million parameters. There are a few 100,000 samples that need to be crunched through. The epochs are several hundred. So if you do the math, you figure out, how long does it take? It's quite some time. Yeah. So, yeah. Okay. Well, that was great for AlexNet. But what researchers figured out, starting with Szigeti in 2014, is that there's a relationship between the depth and the type of network layers and the total depth of the system. And in fact, there's a correlation between how deep and how complicated you make it and the ultimate accuracy. So if we get all the way down to ResNet, which is the one that I showed as the 2015 winner from Microsoft Research, that's 152 layers. I mean, it's an incredibly complex system. Moreover, with the introduction of GoogleNet and TensorFlow, we now start to see very complex intermediate hidden layers, which means that instead of just going convolution to activation to pooling and so forth, there's a split. There's a split and a merge in TensorFlow, which allows them to do intermediate optimization much more so than we were with just a single pipeline. So the message here is that these pipelines seem to be getting more and more complex, which only translates to one thing, which is more compute power. We are now starting to see, I just read some papers a few months ago, which suggest we're going to see our first 1,000 level network. So, I mean, that's an enormously large network. So, in a way, a lot of the researchers have pivoted from how accurate can we make these networks to how much other things we can do. How many other things can we do with this? And so there are a lot of really interesting variations on a theme that are starting to emerge, and what I'll call sort of the advanced network architecture group. We're starting to see compressed networks. In fact, was developed by a Stanford student here, Han, and this was a big breakthrough because one of the ways in which we measure the sort of impact of a system is how many parameters, how many connections, how many layers, how many things that have to be done, how many ops. And what they were able to prove was that there are ways to essentially do away, effectively, with a whole bunch of different connections and parameters and so forth, and this is called compressing the network. They've achieved, on some networks, not all, this is not scalable to every network, but they've achieved a 50-to-1 reduction in parameter impact. So it's a huge, huge improvement. Residual networks are in a class which allow you to do sort of last-minute learning. There's Inception, which I mentioned before, which is the GoogleNet TensorFlow invention. This is very quickly becoming the standard around which a lot of the initial work is being done for application development. Fully convolutional is sort of illustrated at the bottom, where we can break it down and get a classification and then do some work and then really build it back up to effectively give you the same image you had before, perhaps annotated one way or another, but the ability to do convolution in one pass and then deconvolution all the way back up to the original is sort of what we look at for fully convolutional networks. Sparse networks is a similar approach to compressed, and perhaps the biggest focus for the most recent NIPS conference and CVPR is the idea that we now can look at these networks with reduced precision. Almost everything up until this point has been done through 32-bit floats, and while GPUs and CPUs are great at that, it does take a lot of energy and computational power to do that. So a few researchers, starting with Gupta, figured out that we can actually reduce the precision of the parameters at a minimum and end up with almost identically the same accuracy as you would if you did with 16-bit floats or something like that. So this has become a very hot topic for research. There are at least 3 or 4 new networks that have come out, BNN, TNN, I can't remember them all, but the point is that they've discovered that you can achieve the same result or nearly the same result by simply making the precision of the parameters lower. And there is some work being done even on the image input itself to reduce it to a binary type of, even ternary. There's a couple of different versions. Softmax approximation, there's a bunch of functions in there which are computationally pretty heavy. There's a number of different ways to approximate softmax and so forth. So the point here is that there are a lot of really good new areas of research, some of which will get good results, maybe others we don't know. However, the point is that there's a rich amount of research being done to address all sorts of things that we believe might be useful for deep learning. How are we doing on time? Good, we're good. So I mentioned earlier that the cloud gets an enormous amount of information every day, 2.5 quintillion bytes every day. It's 4 million hours of content from YouTube. You pick your favorite sort of topic area. The challenge that guys like Google have just can't be underestimated. I mean, they're building buildings worth of servers to address all of these.
So I have to ask the question because I was at Dave Patterson's retirement in Berkeley. Are you going to get, for instance, I understand the feature and pattern recognition. Are you going to talk about facial recognition?
I hadn't planned on it here, but I certainly can talk about it. I'm quite familiar with it.
I mean,
yeah.
It's the fact that Dave been brought out in terms of the learning stuff, of,
yeah.
The inability for most systems to recognize black people.
So the good news is that if a number of conditions are correct, the facial recognition works well. If any one of several different conditions are slightly off, it fails miserably. Right. So I mean that's the state of the art today. Right.
Three-dimensional models of phase.
Yeah. That's the state of the art today. Pose recognition, whether you're smiling, whether you're not. I mean, all of these things are incredibly difficult to categorize correctly, right? Classify correctly. I think there are a number of researchers who believe that it's just a matter of time to figure out the right training set, because the network itself is perfectly capable of discerning a lot of these different parameters. And the proof of that is in some of the data sets. I apologize for the diversion here, but some of the data sets which actually contain in their training set, 7-degree differences of pose. So you're training the system to know, all of those different poses. And so it's no surprise then that in that particular system, it is able to correctly identify the different conditions around which those conditions exist in the real world. So, but in the general case, no, we're quite far away from that, yeah. Which, by the way, is why Windows Hello uses IR, right? They cannot rely on RGB as the source. They use IR. So.
Yeah, the most recent dabbing one at the CES was the IEEE reporter who apparently had blue eyes. Yeah. And their training set was all people with brown eyes.
Yeah. Yeah. Which is, like I said, which is why Windows Hello relies on IR. I mean, the IR is by far a better, modality for that sort of thing. Yeah. So, okay. So I mentioned Moore's Law plus immersive computing, and so now I'm going to go through a little bit of, talking about what we're doing at AMD, and this is not a sales pitch in any way, but it I think does try to tie what these challenges are with respect to deep learning into what we are doing from a product point of view. So the big data center disruption is sort of where we're aiming at, and I'll go through a very quick sort of series of things. If you look back in the 70s, we had hundreds of mainframes, and we had thousands of mini computers, and we had various versions of cloud computing, and we're now getting into the era where the machine intelligence is going to be measured in the tens of millions of units. And so what does that mean from a compute point of view? It means that while there may be many instances of very, very large server farms, there are going to be lots and lots of compute elements out in the system at the edge or in the network which are participating, and we call this a hybrid type of system, because it's not just a matter of having very, very large servers crunching on all this data, it's also a matter of having the right intelligence at the edge with either inference as a only function or what we call hybrid reinforcement learning. And so this is sort of a cartoon of, we have the classical cloud, the classical, client and so forth. Lots of ways people have done this before. And if we kind of look at where we're going, there will always be sort of the laptops, the personal computers, the cell phones, the engines that everybody uses. But somewhere in between, there's going to be engines that do a little bit more. They're a little bit more heavyweight, and they're more capable of translating things between the cloud and the massive data and the user, which only needs a little bit of data. So now this is sort of getting into what is Radeon Instinct. RTG, the question came up before, stands for Radeon Technology Group. That's the group within AMD that focuses on very, very high compute server class GPU development and so forth. So all of the Radeon products that you see being sold today come out of the RTG group. We also supply the IP, which in its sort of embedded form becomes part of APUs and other products that are sold within AMD as well. So Radeon Instinct is sort of the introduction now of Radeon with the machine learning part attached to it. So we have a number of different things, and if you can imagine sort of the top level, this is a classic stack of what does your product do for different applications. Obviously there are a wide variety of different applications that we will be focusing on. The ones that are already publicly available are, or publicly announced, are Alibaba and Google. And so they're going to be using our high-end GPUs in their machine learning platforms, in their cloud computing systems. So there's a wide variety of applications. We have a number of ways in which we are optimizing the frameworks and the support for application development, much the same way you would see an application framework in almost any other kind of software stack. We have what we call the ROCm the Radeon Open Compute ROCm software platform, and that's our standard set of compilers, linkers, debuggers, assemblers, everything you need to put together a software system and deploy it. And then underneath, there are a number of different ways in which we target various platforms, and I'll talk about those in a minute, but the idea here is that we have a common set of software that sits on top of any number of different types of hardware. And these hardware platforms are not necessarily totally interchangeable. So for example, the kinds of things that we put on the small cards for local GPU type compute are different than the kind of things that we put on the large cards, mainly because of the need to have very rapid memory interchange between devices. So this is a very simplified view of things. There's a training part of deep learning, and then there's an inference. Training takes an enormous number of samples, both positive and negative, to help the system determine the best set of parameters. This can take minutes to hours to days to weeks, depending on how complex it is. And then once those parameters are generated, they can be deployed on a system that may have some real-time input video or something like that. And the idea is to get that down to milliseconds to seconds before you can get a classification output. This is something that can be run on multiple GPUs, a single GPU, a CPU. It really doesn't matter. It's rather generic in that sense. So I'm going to talk a little bit about the software part of this. Our software approach is quite different. We have taken the idea of open source and really expanded that to a number of different places. We were one of the original founding members of the HSA, the Heterogeneous Software Foundation, and we have really pushed this idea to the point where it's open source for almost everything. There are very few things that we have in our software stack which are proprietary. And the only reason they're proprietary is that it doesn't make any sense for somebody to have it because they wouldn't know what to do with it. The Radeon Compute Platform consists of several vectors. We are always interested in performance. We have a number of different ways in which we can target different hardware, different software applications, and match them according to the optimal performance metrics. It's open in the sense that people who sign up for it and use it can contribute. We have a way to review all of it and make sure it gets validated properly, but the idea is that we want the community to participate and to generate contributions. And then we have the notion of hyperscale, which means that this is built to serve a number of different, everything down from the lowest, smallest card all the way up to massive server class machines. And in fact, this is what our customers at Google are using. So this is more detailed. I don't think I'll go into a whole lot of discussion about it, but the point is that we have assembled together a rather large team to put together all of these capabilities. We have already released, I believe, ROCm 1.5 now. I don't recall the latest one, but it's something like that. And we're on track to release something like once every other month or so. We target various types of hardware. This is just a schematic of how the various code generators work. We use extensively LLVM, and the idea is that through this sort of closed-loop compiler work, we get a reasonably good code generator for the language runtime and ultimately into the system. I'm going to talk a little bit about where does deep learning fit in this, because this is really a generic way to look at it. Turns out that there are some really interesting things that have to be discovered and dealt with in the API. So this is what we call the MI open stack, and this is the part that fits inside of ROCm. It has a number of different layers, including support for a variety of different frameworks, starting with TensorFlow, or Caffe rather, and continuing with TensorFlow, Torch, Theano, MXNet, and so forth. We have a number of middleware components. There's a standard MI open API which deals with putting together networks, the communication among different layers of the network, and then there are a bunch of math libraries, BLAS and FFT and so forth. It turns out that the math required for almost all of the convolution layers can be in some part using the standard BLAS libraries and so forth. We're starting to experiment a little bit with the trade-off between FFT and spectral types of convolution. It turns out there that there are some cases where it's very successful and other cases where it doesn't work very well at all. So the point is that we have a number of these packages either in development or already there. There's a special package that we have that is designed to acknowledge the idea that there's a large installed base of deep learning software that's not compatible with our hardware. And that's a package called HIP. And HIP is designed to take code that was originally generated using CUDA and CUDNN, and it translates it back to the native HCC environment. And so we have the capability now of essentially porting code that had its origins in a proprietary environment into an environment which is totally open. And this is a very powerful tool. We've now had quite a few months worth of experience using it. It's hugely successful. We have been able to sort of transpose hundreds of thousands of lines of code in a matter of minutes. I mean, it's just a remarkably efficient engine. Whereas if you were to ask a software programmer to say, all right, take this code and then generate it for HCC, you can only imagine how long that would take.
What's the runtime efficiency? So your hardware really running it faster or slower?
So we ran some experiments. It's a good question. I mean, we're still gathering data, but the anecdotal evidence is that there are many cases where it actually runs faster once it's been converted into HCC style, even on the other hardware. So,
why would it run slower?
I don't know. I mean, I don't know. Yeah.
It's
We just record the data. Yeah. So these are just different examples, ways in which we combine them. All of our GPUs require connection to a CPU of sorts, and the normal way in which we do it is through PCI. The next generation type systems are going to use a combination of PCI, XGMI, and CCIX. So if you look at deep learning from a sort of how would you choose the platform to now look at ways to work, ways to make this work on a hardware system. From a purely abstract way of thinking, you can say, well, if I've got lots of stuff I need to do, and deep learning happens to be one of them, I'm most likely going to want to put it on some sort of a general purpose core, only because if I can't run the other stuff on a GPU, then I'm stuck. I don't have everything I need. Conversely, if all I ever needed was one little piece of a deep learning algorithm, I might pick an FPGA or a semi-custom type device. but that is the only thing it will ever be able to do. So the compromise is that you can, find lots of examples where the general purpose cores are the right answer, and the GPU is the other right answer, depending on what your mix is between focusing on things that are strictly deep learning or strictly GPU capable versus things that might require other types of calculations. So that brings us now to the products themselves. And the first one is Zen. You may have read a little bit about some of our recent announcements. And we're getting ready to actually start shipments. I think the target is sometime this year. I don't know the details, but I can tell you that the progress that's being made and bringing up the systems and getting everything going is on track. They're doing a really good job. So what is Zen? Well, Zen was started many years ago, probably 4 or 5 years ago, as a completely ground-up new design for x86 compatible type system. And the idea there was to anticipate that we were going to run into trouble with Moore's Law, that we were going to run into some really difficult challenges with respect to geometries. Power was going to be a challenge. And so all of these things were on the table and part of the sort of requirements document for Zen. And we also know that SMT, multi-threading, was coming along. It was not, this was something that both Intel and AMD had been pushing for some time. The reality is not many applications were adopting it. So we believe that this is about to change, and things are starting to heat up a little bit on SMT front. And also a new memory system. So the cache system, the hierarchy of memory, the way in which memory is shared among the various cores, all of these things were on the table. So, and the last thing, of course, is to incorporate FinFET technology and build in power-efficient designs to the system. The result is that we achieved a 40% uplift on IPC and a corresponding lowering of the power per clock level. And so this is a huge development because it's the first time in many, many years where you see the difference between one generation and the next generation to be so big. So we're really excited about this, and like I said, the testing that we've done so far is looking really, really good. So, yeah.
How many threads do you run simultaneously on a core?
Good question. I want to say 10, but I'm not confident about that number. It's up to 10, yeah. I think it's up to 10. I don't recall exactly, but I know that, the typical numbers are 2 and 4. Because it's so hard to do the context switch. Yeah, the context switch is automatic in hardware. Yeah, right. Yeah. I'm sorry?
Is it like hybrid threads?
Don't know. So I'm not a CPU guy, and I'm sure Mike or one of the other guys could help you there. So sorry.
What's this instructions for clock order of magnitude?
You mean what's the absolute number?
Just an order of magnitude.
No, for about.
Oh, how many do we get now? Oh gosh. It's kind of like high single digits. I recall. I don't know the exact number. It's not 20. I mean, if we were 20, we would be competing with GPUs. Yeah, I think it's high single digits, but I don't take my word for it, please. Yeah. It's an order of magnitude, yeah. Less than 10, more than 1. Yeah. Okay. So just a sort of laundry list of sort of benefits and performance. Like I said, a lot of work in the memory system and ways in which we order queues and loading and swapping queues for instructions and so forth. A lot of very, very clever ways in which things are handled in the inner parts of the pipeline. The improvements to the L1, L2 caches are pretty big, but the big one is a L3 bandwidth was increased by a factor of 5. So. Mhm.
Here it says 2 threads per core.
2. All right, so that's the right answer. Yeah.
Okay.
Like I said, I'm not a CPU guy, so you can't, I'm sorry? It's 10 base 2, yeah. So, yeah, right. And like I said, lower power. So we have a lot of things that are in here that are really, really impressive. This was a fairly large design team that did this, and well, they're still working on it, but it's a remarkable new product that's going to come out this year. So it's just a kind of a picture of the overall architecture. There's 4 ALUs and 2 address generator units. So yeah, I don't know if it tells you any one of those numbers that might be interesting. Yeah, I can have 192 instructions in flight, so that tells you a little bit about what sort of the complexity of the state machines internally is. So. And so the other piece of this, of course, is that we can gang cores together. So this is an example of a 4-core system with each core having its own L2 and then sharing L3 memories. And we expect that this will be sort of the baseline for a lot of the high-performance server class systems coming forward. So Radeon Instinct is the machine learning part of the GPU, which I'll switch gears and talk a little bit about now. And while we have a fairly long history of doing GPU development products and so forth, this is the first time where we're now starting to identify specific GPUs for the purpose of accelerating machine learning. So this is sort of our roadmap for the various versions of GPUs over the next couple of years. Last year we announced and shipped all of our Polaris systems, so that's the Fiji class systems. And so those are currently in production right now. Vega is on the bubble, and we're getting ready to let that loose as well. There's several versions of Vega in design right now. Interestingly, this is going to be the first one that uses HBM2. HBM1, I think, had a bandwidth limitation of about 256 gigabytes per second, and I think HBM2 bumps that up to like 512. And then Navi is the sort of next generation after that. It's sort of the next generation of the graphics core that we'll be using after Vega. So one of the big things that happened between Polaris and Vega was, again, IPC improvement. And so we used to have this alternating op in the previous generations. And now we've doubled up and improved what we call NCU, the next generation CU, to execute 2 ops every cycle. So that's the basic improvement that was made there. Lots of other improvements in routing memory locally. There's an enormous challenge to figure out how to get a large number of cores to be mapped well with the memory architecture and the throughput. Those are all big challenges, and some pretty big improvements have been made there. So the deep learning, or the what we call machine intelligence versions of these, are called MI6, MI8, and MI25. MI8 is sort of the next version of the Fiji class system that's coming out. And we already have a couple of these shipping in different configurations, and then MI25 is sort of the near-term version that we're preparing now with Vega. The idea here to show the teraflop ranking or rating here is only to give you a sense of what sort of overall capability is. There's a theory that was developed at Berkeley called the roofline model, which tells us about how we can anticipate the best throughput on a GPU based on the memory and what we call the arithmetic intensity of the operations per byte. And it turns out that the higher the operations per byte is, the more likely that you'll reach these maximum throughput. Otherwise, you're going to be on the slope going down. Got a few more left and we'll be done. When we combine it with Zen, we end up with a fairly powerful system that either one or more GPUs can be combined with a Zen processor. And you can imagine now the types of configurations we can put together that do both general purpose processing for all sorts of high performance compute server applications, as well as deep learning that are targeted directly for GPUs. And then finally, when we put together the software that we talked about earlier, heterogeneous computing with our ROCm software stack, that we believe is sort of the three parts of the picture that put all of this together, that give you the sense of very, very high performance in a variety of different application platforms. So, and that's it. Questions?
How does the hardware for learning relate to the hardware for recognizing or for classifying?
Good question. Yeah. So I didn't really cover that. What's the difference between training and backpropagation and inference and so forth? I did mention that there are shortcuts that we can take on inference, but we cannot take those same shortcuts on training. The reason being is that the backpropagation function relies on stochastic gradient descent. And the stochastic gradient descent, while it's one of the simpler versions of gradient descent, that's a first order gradient descent algorithm. There are higher order gradient descents. However, to do that properly, we need floating point accuracy. We cannot do this without floating point accuracy.
You may need the floating point in the learning.
Yes.
Not in execution.
That's correct, right.
Interesting.
Yeah. It turns out, if you think about it, the sort of theory behind gradient descent is that you want to make tiny improvements to each parameter each time through the system. And those tiny improvements have to be resolved at floating point like accuracy. Yeah. And if you go to second order like BFGS or something like that with Hessian, you even have more. It's much more complex. Yeah.
You have?
It turns out that we can do it with 16-bit floating point. Yeah. FP16 is sort of the standard these days. Yeah. Yep.
These days, Google seems to be saying that 16 bits is enough.
Yeah. So
the parameters for the parameters.
yeah. So like I mentioned, right. So like I mentioned, we are working on several initiatives to even go below that. We think it's closer to 8. The paper by Gupta clearly shows that at 8 bits we can get within striking distance of accuracy that nobody's going to care about. So yeah.
This isn't an apples to apples comparison. So, in a biological neural network, in a pigeon brain, for
sure.
instance,
Yeah.
The neurons, axons have weighting factors that evolve over time, which I think are on the order of 8 bits.
Yeah, I seem to remember that. Yeah.
Maybe
Well, but it's even more. The bigger factor there is what's the activation function. The accuracy of the neuron itself isn't really important, or the weighting factor of the interconnect between neurons. The most sort of important factor to consider in the biological sense is what's the activation function. And that's where things like RNNs and LSTMs are becoming more, looking more like neurons, because there's a forget gate. Neurons in the brain don't always behave the same way all the time. They evolve over time. They evolve as a function of neurons spiking density. They respond to, how much information overload you're getting, things like that. And that changes over time.
In a way, that's often a good thing, I think,
Yeah.
in the sense.
Yeah,
that
otherwise your brain would explode.
Noise into the system such that the brain is not a deterministic system.
No.
It's always identified the same
Well,
thing.
more than that, it's a self-forgiving thing. If you were observing and absorbing all this stuff all the time, your brain would explode, right? You just, overload. So over time, your brain trains itself to say, well, I'm only looking at stuff that's important, otherwise I'll get way confused. So LSTMs are a lot like that, yeah. Yeah.
So you're building headless GPUs, basically,
Yes.
with no gravity. What do you get to leave out? Do you get rid of the frame buffer? Do you get rid of the 4x4 multipliers?
In the GPUs, you mean?
Yes.
So no, the GPUs have, so it depends on which one you look at. If it's just a server class, yeah, we kind of leave a lot of that stuff out. But almost all of our GPUs, for example, that are, that plug into, desktops or whatever, they all have frame buffers, they all can run 4K video, they all can do, compression, these sorts of things. So we include all of that on the DGPU die itself, yeah. But in a larger class system where you only care about, compute power, yeah, we don't need a lot of the multimedia stuff, right? Yeah.
The 60 million parameters number that you gave out?
60.
60.
Yeah. That's for AlexNet, yeah.
Right.
Yeah.
So that's like for an older
Yeah.
design. So
Yeah.
with one of these 1,000 layer networks, how many parameters are we
So,
talking?
so the current Google numbers that we have seen are about 1 billion. So, billion parameters.
To train, you have to
You have to optimize 1 billion parameters, right?
across all layers.
All layers, all inceptions, all that stuff. Yep. Yeah. It's mind-bogglingly large.
So if
Yeah.
you have 1 billion parameters to optimize, how much training data do you need?
Hundreds of millions of samples.
And what kind of problems is this?
This is mostly for image recognition. So if you went to Google, you say, I want a picture of a mountain scene with a lake with a plane circling around. That's what it would search for. It would do a search for classification, and it would find it. Yeah. Yeah.
Turning things back a bit, at the very beginning of your talk, you mentioned the cost of doing a tape out.
Yeah.
For a modern day processor.
Yeah.
Millions, tens of millions of dollars
Yeah.
or whatever. How many masks about are involved these days and that sort of thing?
I don't know. I mean, I know that in the sort of, in like 28 nanometer, it was north of 50. But I don't know what it is today. Yeah.
I'm hoping that the chip designers have developed some sort of methodology or philosophy or architecture such that a huge class of potential bugs do not require the full set to be read.
So actually, we're starting to use deep learning for that. Yeah.
Okay.
I mean, when think about it, we right. Yeah. That's the problem, right? When you think about it, these chips have multiple billions of transistors, right? So if you were to ask a designer, what does that transistor do? How would he know?
So I'm confused. Are you saying you're using deep learning to try to avoid having to fix bugs, or in terms of how to design the chips?
We different.
Bugs can
So there's a new class of tools coming out called HLS, high level synthesis, and HLS is designed to take C code in as a model, and then translate that to the appropriate transistor and layout for the design, without ever having to touch the lower level of abstraction. So now the challenge is to make the C model have the proper regression so that it can be validated properly. It's a lot easier to do that than it is to do an architecture model and figure out how to test and regress each of the models inside the hardware. Yeah. I mean, we're kind of in transition. I mean, the industry has not quite caught up to all of that, but that is the direction everybody's going. So.
Except that layout will have bugs too.
Yeah, It's a complex, yeah. I mean, that's why it's so expensive, yeah.
I
So,
was actually hoping your answer would be a lot more fundamental to that, something along the lines of having tremendous flexibility with just the metal layers, or having, filling all the empty spaces with PLAs that you could tap into later in order to add new functions.
they do a little bit of that today. I mean, that's not a new idea. There are certain functions that can be fused one way or the other, things like that. There's a tremendous amount of flexibility in how we toggle the power islands and so forth. So some of that's already there. I don't know the degree to, how extensive it is, but I know some of it's already there, yeah.
Are you getting rid of your designers?
No time soon, I don't think. No, yeah.
You didn't disclose the lithography for Vega, or was that by design?
Yeah, I think that that's not public information, so.
The last one before that was already 14 nanometer?
Yeah, Polaris was on 14, yeah. Sure, go ahead.
Getting really far afield. Questions. Seems like for 25, 30 years, AMD has often controlled maybe 15% of the x86 market, or rather Intel has controlled maybe 85%, and AMD is. And it's almost like a constant of nature that no matter what happens, AMD falls a little and then catches up, or Intel takes a lead and then screws something up and loses market share again. Do you think that's, after so long, so consistent a ratio, do you think that's an accident?
And I'm supposed to answer that? Jeez.
That's a neural network.
Question after the camera.
Also, I might point out that there's a long history of antitrust case law that says that to control monopoly power, a company that only has 85% of the market cannot be accused of having monopoly power. So Intel's sure been lucky in that regard.
I have nothing to say.
Off topic. It's coincidence, I don't know. Yeah, so.
Kind of a serious question along those lines. I mean, right now, the other guy has a huge lead on the deep learning.
Yeah.
So what is the plan? Is the plan to sort of get to 10% market share possibly? Or, I mean, you're probably closer to zero right now.
How do I answer that? I think the best way to state this is that, we have some very smart people, and we have been able to observe what's going on, pretty thoroughly. We believe that we are in the very, very, very early stages of this market. 100% of a market share that 5 years from now might be 0.1% of the total market is something that we're taking into account. So, yeah, I mean, I think you can make those observations, but I think we have a pretty good idea of what is emerging as the drivers for this market in terms of requirements, and we're responding to requirements. And I think that's the best way to put it. Pace. So the challenge here is, what do we do with all that data, and how do computers in the server class systems deal with that kind of data challenge? And it's not just the amount of data, it's the timing, it's how quickly can we turn that around and give us a result that we're looking for. The poster child for this, of course, is Google, where every single query that you make goes through a series of deep learning inference kinds of decisions, and over time it learns how to give you the best query in the quickest time in the right order of importance. That's all an example of deep learning. It's under the covers, nobody knows about it, but in fact it is deep learning in a very, very large scale. So with that in mind, I'm going to cover 5 topics. I apologize ahead of time that some of these are going to be rather abstract because I don't have enough time to get into detail. However, it's suffice to say that we believe we've done our homework. We believe we have looked at the problem closely. We have evaluated all of the parameters that are available to us, and we certainly recognize some of the limitations that exist. So I'm going to go through compute trends and challenges. This is not specific to deep learning, but deep learning is sort of the customer of what it takes to do all of this. And then I'm going to talk about deep learning opportunities, and with the idea that every one of these opportunities creates a demand or some kind of an ask on the side of computers and software and algorithms. So we'll review that for a little bit. And then finally, to tie it all into the kinds of products that AMD is doing with respect to our software stack, our two different classes of hardware, mainly Zen, which is the x86, and Vega, which is in our GPU class. If you have questions, I'd be happy to answer them. However, I guess the best way to do this is to perhaps wait until the end. Is that, Andy, is that okay with you? Yeah, that's my choice. All right, well, whatever. I'm easy, so don't be afraid to. Okay, so this is sort of a cartoon, really, of data points that reflect where we are in various metrics with respect to computing. And the details aren't really necessary to understand, but what is interesting to note here is that everybody's sort of said, well, Moore's law is sort of over, and we're getting to the point where we just don't get enough bang for the buck anymore the way we used to. The amount of transistors per square millimeter is leveling out, and so forth and so on. And this is all generally true. More importantly, we're reaching a point where we can't run these chips any faster. We're at several gigahertz now. It's just not possible to run them faster without sacrificing something else, and usually that something else is power. There have been many attempts to sort of scale it in a different direction by going into multi-threading and multi-core and so forth, and you can start to see that emerge right around 2010. And certainly there's some success there. We wish there was more, but the fact is we have enormous amounts of legacy code which doesn't fit well into the multi-threading kind of multi-core approach. However, it's there for the taking, and we get a certain amount of benefit out of it. The next issue is cost. I actually can remember the days when, if we tape out 180 nanometer, we thought, wow, that's really expensive. That's $5 million. Today, those numbers are long gone. So we're in the age now of 7 nanometer. There are some experiments and some work to go even below that. The fact is that this is what it takes to be competitive in the advanced semiconductor world. And AMD participates in this as aggressively as anybody else. But the problem is that, as you can see, and this is really just a relative scale, but the cost to do this is quite significant. It's many tens of millions of dollars to do a tape out these days. So you can't get it wrong. You have to do it right. And that means that we have to do enormous amounts of work on the front end to do the regression and validation. So welcome to Moore's Law Plus, and the idea behind Moore's Law Plus is that, well, we acknowledge all of those things we just talked about, and then build on the idea that we'll start turning other knobs, right? We'll turn knobs on integration, we'll turn some knobs on process integration, or process technology. We will definitely turn knobs on system design and software, and we will, treat it as a whole to build different types of systems using the building blocks that we have from the traditional way and some of these new ideas that are intended to help us through the system integration problem. So there are a number of different ways in which we do this. I won't go through this in detail, but the point is that for each one of these ideas, we've developed a shopping list of sorts that can help us. And I'll go through a couple of examples, but it's important to note that, we are not afraid to say, all right, yeah, Moore's law might be sort of dead or not moving as well as it used to, but we're going to be just as aggressive to move in directions which help us build bigger, better, more higher performance and lower power systems, despite some of the limitations that exist as a function of the traditional Moore's law. So obviously the foundation for all of this is sort of the underlying silicon technology. There's a lot of work going on to figure out how to do this better, how to build more advanced. Thank you, and first of all, I like to say I appreciate coming here. I've always enjoyed coming to Stanford events, and certainly I think this promises to be an interesting time because obviously you all have a very keen interest in this, and it's something that we at AMD take very seriously, and we think it's got a huge future. So, first of all, just to introduce myself, I'm a fellow at AMD. I focus on three different things: imaging, computer vision, and deep learning. I'm the domain architect for all of those, and which means that I more or less innovate the various architectural approaches that we want to take on the various platforms that we provide to our customers, both on the hardware side, the architectural side, and the software side. So I'm deeply involved in this. Originally, Mark Papermaster was supposed to come, and unfortunately he had some other obligations, so he asked me to step in, and the only reason I'm mentioning that is that he is by far a better speaker than I am with respect to what we do in the various products that we have, namely Zen, Vega, Navi, and beyond, and so forth. He can speak about those much better than I can. But the talk here today is about really more on deep learning as it relates to Zen, Vega, the architectures that we have coming up and beyond, and how we think about the various challenges that exist in deep learning, not just at the big scale, but at the small scale. So there's lots of really interesting topics, and what I'll try to do over the next hour is to try to give you an overview of this. This is by no means a technical deep dive. I do have some material on that, and generally those talks go for several hours, but this is more to try and understand, what the relationship is between the challenges of deep learning as they exist today and how we expect them to evolve over time, and the kinds of compute power that we have available to address them and to provide users with reasonable experiences and reasonable outcomes. So, before I get to the agenda, what I thought is maybe talk about some of the things that we actually want to experience. So deep learning is a very abstract thing. You want to give it some data, you want to teach it something, and then you want to be able to extract classifiers and so forth. And that's all interesting, and for those in academics, that's the thing that we really focus on is the errors, how many epochs, what's the training converge rate and so forth. But for general users, what you really want is the demand for better experience. And so there's a couple of examples here, and everybody's familiar with VR and sort of the new age of experiencing what we call embedded imaging or immersive imaging and things like that. So the question then is, what does it take to give you good experience in those kinds of environments and those kinds of applications? And while that may seem a long way away from deep learning, it actually has some very, very close kinds of things that require the development of useful products and capabilities within these experiences. So while it looks simple and everybody's done it and sort of experienced it, getting it good and getting it reliable and getting it robust is actually pretty hard. So this is one example. The other example is that we are kind of in an age now where there's this mounting demand for compute power and capability to handle very large data sets. And this is not going away anytime soon. The advent of the internet with the ability of high bandwidth communication to and from the cloud gives us the sense that, you know, the amount of data that's going to be there and available is enormous and growing at a very, very rapid